Welcome to the next lecture in this pattern recognition video course. We have been looking at EM algorithm last class. So, let me recap the entire context. We have been looking over the last few classes on ML estimation of mixture densities. Okay. The last class we considered the maximum likelihood estimation of mixture densities, and we specifically consider the example of learning a mixture of Gaussian densities. Of course, the technique is very general and it can be used for learning any mixture of densities. The example we consider, however, is a mixture of Gaussian densities. So, we actually looked at only mixture of two Gaussian densities. We obtained an iterative algorithm to maximize the log likelihood. What we did is, for the mixture we actually calculated the log likelihood, then found all the partial derivatives, equated them to 0, got a system of nonlinear simultaneous equations and derived an iterative scheme by using a Gaussian way of solving simultaneous nonlinear equations. Okay. Then we introduced the concept of EM algorithm and showed that the iterative scheme that we got is actually an instance of the EM algorithm. Okay. So, we looked at the EM algorithm in detail last class. So, this class I will once again briefly recall the EM algorithm and then look at EM algorithm in general and a few convergence properties. Okay. So, let us recall the EM algorithm. As I said, the kind of situations where the EM algorithm is used is for estimation problems, where we think of the given samples, the IID samples we have from the density as incomplete data. They are incomplete because we can formulate what we call missing data, and we formulate the missing data in such a way that had we been given the complete data consisting of both xi's and zi's. So, the incomplete data is x1, x2, xn, that is given to us as data. We formulate some missing data which we call zi, zi I is equal to 1 to n, and then the idea is that if we are given the complete data xi, zi, then the estimation is very easy. Of course, we are not given zi, we are given only xi, but if we can formulate missing data zi like this, then we can think of it as an estimation problem, where actually if we are given xi, zi, we know how to estimate, but we are not given zi, can we still estimate? The EM algorithm is a very general purpose iterative scheme for handling that kind of maximum likelihood estimation problems. Okay. Maximum likelihood estimation problems where the given data is viewed as incomplete, and had we given some extra missing data, the estimation would have been very simple. Given these two situations, EM algorithm tells you how to get those estimates knowing only the incomplete data and the formulation of the missing data. Formulation in the sense of the probabilistic model that governs the distributions of the missing data. Okay. As I said last class, it consists exactly of two steps, expectation and maximization. That is why it is called EM algorithm. EM stands for expectation and maximization, or expectation maximization. Let us once again recall the two steps. What are the two steps? First step is expectation. In the expectation step, we compute a function q theta theta k. Theta k is the current iterate value of the unknown parameter theta that we are estimating. So, we compute a function which is a function of the general variable theta and also of the current values of the estimated parameter. This is computed as an expectation of the complete data log likelihood. Complete data is xi, zi, is computed as the expectation of the complete data log likelihood, where the expectation is with respect to the conditional distribution of the hidden or missing variables, that is zi, conditioned on incomplete data, that is xi, and the current value of theta is theta k. Okay. In symbols, q theta theta k is expectation of z conditioned on x theta k of ln f x z theta. Note that the complete data log likelihood ln f x z given theta is a function of theta, and there will be some terms there which are which involve z, some terms which may not involve z. The expectation is, we are taking expectation as averaging out only the z's, the x's will remain. Wherever there is a z factor there, we are going to average it out using the conditional distribution of z conditioned on x and theta k. So, those parts that are expectation out, they will be functions of theta k. There can be other parts which are functions of theta, that is why q is a function of both theta and theta k. So, the first step in EM algorithm is in each iteration, given the current values, value of the values at the current iteration of the unknown parameter estimate, we compute this function q theta theta k, and then the second step, the so called maximization step or the M step, having computed this function, we then compute the next iterate value, that is theta k plus 1 at that value of theta, which maximizes this function as a function of theta. So, you are asking treating theta k as constant, we try to maximize this over theta, and the value of theta that maximizes this is given as the next iterate value in the estimation. So, in symbols, theta k plus 1 is the argument, that is the theta that maximizes the function q theta theta k. Let us briefly recall our example. What was our example? We have considered estimation of two component Gaussian mixture, where the probability model is f x given theta is lambda 1 phi x given theta 1, lambda 2 phi x given theta 2. Phi x given theta 1 is normal with parameters theta 1, that is theta 1 involves mu 1 and sigma 1. Similarly, phi x given theta 2 is normal with parameters mu 2 sigma 2. So, theta 2 is mu 2 sigma 2, and lambda 1 lambda 2 are the mixing coefficients. So, theta consists of theta 1 theta 2 lambda 1 lambda 2. Okay. This is our model, and we have data xi generated according to this model. Then we have to formulate our hidden variables. So, we formulate hidden variables as Boolean. So, for each xi we have a 2 component Boolean vector, the 2 component Boolean vector because this density model is 2 component. So, Zi 1 and Zi 2. The basic idea is that they tell us whether xi, the ith sample, came from the first component of the mixture or second component of the mixture. So, that Zi 1 is 1 if it has come from the first component of the mixture and Zi 2 is 0, and if it has come from the second component of the mixture, then Zi 1 is 0 and Zi 2 is 1. Okay. So, this under this formulation of the hidden variables, the following distributions are immediate. Firstly, the marginal of Zij's, probability Zij is equal to 1, Zij's are binary variables. So, the distribution only we need probability Zij is equal to 1, that is lambda j, because lambda j is the probability with which it will come from the first component. And if you tell me Zij is 1, that means I know xi has come from the first component, then the density of xi is simply phi xi given theta. So, conditioned on Zij is equal to 1, that is coming from the jth component, then f xi given Zij is equal to 1 is phi xi given theta j. Okay. Matter of fact, the way we have written both these equations is easy to see that it easily generalizes to k component mixture. The Zi will then have Zi 1, Zi 2, Zi k, and these equations will still hold for j is equal to 1 to k. Because Zi is vector of these 2 binary variables and only one of them will be on at any given time, I can write the mass function of this Zi as f Zi given theta as product of lambda j to the power Zi j, that is lambda 1 to the power Zi 1 into lambda 2 to the power Zi 2. If Zi 1 is 1, then Zi 2 is 0, so this becomes lambda 1 and vice versa. Similarly, f of xi given Zi comma theta can be now written as phi of xi given theta j to the power Zi j product over j is equal to 1 to 2. Once again, when Zi 1 is 1 and hence Zi 2 is 0, this becomes phi xi given theta 1, and when Zi 2 is 1 and Zi 1 is 0, this becomes phi of xi given theta 2. Okay. So, this is the marginal of Zi, this is the conditional of xi given Zi. So, if I want the joint of xi and Zi, I have to multiply them. So, that will give me the density model for the complete data. So, the complete data density is given by f xi Zi is product of these two. So, I here have lambda j to the power Zi j, here have phi xi given theta j to the power Zi j, I multiply them, I get lambda j phi xi given theta j to the power Zi j. Okay. This is my complete data density model. Now, what will be the log likelihood? The likelihood will be product of this over I is equal to 1 to n. So, likelihood will be product I is equal to 1 to n, product j is equal to 1 to 2 of this. When I take log, both of them will become sums. So, I get sum I is equal to 1 to n, sum j is equal to 1 to 2, and when I take log of this, I get z I j ln lambda j phi x I given theta j. If you recall, when we had taken the likelihood of the incomplete data, that is the given data alone, x I alone, then we were getting a sum inside a log. We are getting lambda 1 phi x given theta 1 plus lambda 2 phi x given theta 2 inside log, and that was what is complicating our estimation. Now, as you can see, that has changed to, instead of log of a sum, we got sum of logs, and once again if phi is in the exponential family, then this ln can be easily simplified. That is essentially what the formulation of the missing data has done for us. It is in this sense that given the missing data, the estimation is easy. Okay. Given this, what will be my E step and M step? Under the E step, we have to get q theta theta k. So, we have to take expectation of this with respect to the conditional density. So, if I put expectation, it goes to the first sum, second sum, only the z I j's go on to the expectation, because the expectation is for the j's, this ln lambda j phi x I given theta j is a constant, that comes out of the expectation. So, that gives me q theta theta k is the two summations, expectation z I j given x comma theta k into log. Okay. Now, in the last class, we have seen how to calculate this conditional expectation in this case, and that gave us the so called gamma I j theta k, right. This becomes only a function of theta k, gamma I j theta k ln lambda j phi x I given theta j, and this is the gamma I j's. This is the same function that we got when we actually differentiated the log likelihood of x I alone. So, the idea is that now, see, because of this expectation, these expectations are what gave us gamma I j, but the expectation is conditioned on theta k. So, this gamma I j's have now become only function of theta k and not of theta. So, the only function of theta is this factor, and thus maximizing q theta theta k with respect to theta becomes very simple. If with respect to any component of theta I want the partial derivative, then the gamma I j theta case will be constant. I have to only differentiate this. That is like simply estimating, doing ML estimation of a single density. Okay. So, under the M step, we have to maximize this over theta. We can expand this now. We know phi is a Gaussian with the mean mu j and variance sigma j. So, I get this. Okay. The gamma I j remains. So, now finding del q by del mu j or del q by del sigma j is very straightforward, and by equating them to 0, I will skip the details because we done all of that last class. We had got this final equations. These are the final iterative equations that give us the estimate. So, these are the iterations of EM algorithm for this example. Okay. So, let us sum up the example. We saw how to implement the two steps in the case of a Gaussian mixture model. Okay. The Gaussianness of the model only helped us to get the specific forms for the densities, right. Otherwise, up till this point, or rather up till this point, right, we have not used any fact that these are Gaussians, right. For any two component mixture of phi x I given theta 1, x I given theta 2, this is still true, right. So, if phi is any other density, it is still easy enough to calculate the ML estimates, right. The gamma I j still turn out to be the same, right. For any mixture density, I can use the same missing data model, I will get the same gamma I j theta case. Only thing that may change is the form of phi x I given theta j will change. As a matter of fact, not all phi's need be Gaussian, all phi's need be even the same kind. They can be a mixture of Gaussian, exponential, whatever. This is what we get, and as I said, because this gamma I j's are only function of theta k, for any density model here, maximizing q theta is a easy optimization problem. So, we saw how to implement in the Gaussian mixture model, but what we have done is very easily extendable to the case of a mixture of k Gaussians as well as mixture of a k component mixture of any other densities. Okay. We derived the EM iterative scheme for that particular 2 component Gaussian mixture by actually taking the log likelihood of what we called incomplete data. That is what we would have normally done in the ML estimate, and then differentiating it and equating the partial data to 0. Okay. We actually obtained the iterative scheme, an iterative scheme for obtaining the ML estimates, and then we saw that it is same as what is given by the EM algorithm. So, in addition to this example telling you how EM algorithm works for mixture density estimation, it also showed you that at least in this particular example, the EM algorithm is same as actually maximizing the original log likelihood that maximum likelihood estimate is supposed to maximize. So, in some sense, at least for this example, we have showed that EM algorithm is correct. Okay. But let us see this in the general case. So, the next question is, okay, in the general case, why should EM algorithm work? So, let us once again recall what the EM algorithm is. It is an iterative scheme. At each iteration, I have the current value of the parameters, which I call theta k, and then I calculate theta k plus 1. To calculate theta k plus 1 from theta k, there are 2 steps. There is the E step, which computes q theta theta k as conditional expectation of the log likelihood of complete data, where the expectation is taken of the random variables z conditioned on x and theta k. And the M step, where this q theta theta k is maximized over theta to get me the next iterate theta k plus 1. Okay. So, the question is, why should this procedure work in general? We have seen, of course, for the 2 component Gaussian mixture, this procedure is exactly identical to maximizing the log likelihood, but in general, can we say this procedure works? What do you mean by the procedure works? Our overall objective is to find the maximum likelihood estimate of theta, right, given samples x1 to xn. So, if I just computed the log likelihood with samples x1 to xn as the function of theta, and then maximize theta, that is my ML estimate. Okay. So, hence what we want to do is to maximize the log likelihood ln f x given theta, where I hope you still remember that our notation is that the bold x stands for the data x1 to xn. So, this is what we want to do. Okay. So, we have to show that the EM algorithm actually maximizes. What we will now show is that in each iteration of the EM algorithm is like a gradient ascent on the log likelihood. That is, each iteration of the EM algorithm improves the log likelihood. Each iteration of the EM algorithm increases the log likelihood. So, this at least shows that each iteration going in the right direction and log likelihood is monotonically increasing. It is not a complete convergence proof, because even if it is monotonically increasing, it may taper off to a suboptimal theta k. So, to in addition show that all stopping points of the algorithm are actually local maxima of the log likelihood, we will only show this. The rest of the proof is a little technical, but that we assume for now. So, just showing that each iteration improves log likelihood does not necessarily prove that the EM algorithm converges. So, even though we are not showing you the complete convergence proof, we would like to state still that under fairly general conditions, EM algorithm can be proved to converge to a local maximum of the log likelihood function. Of course, what we prove should give you sufficient idea why it should happen, because you are showing that each iteration is like a gradient ascent on the log likelihood. Okay. Okay. So, let us see how to prove this. So, first let us write the conditional density, that is what we are using for taking the expectation in the each step. So, conditional density of z given x theta is by definition joint of x and z by the marginal of x. This is true for every theta prime, no matter what theta prime I put. This is just the definition of any conditional density, which means if I can take f x on this side, it becomes f x given theta prime is f z x given theta prime by f z given x theta prime. Then if I take logs I get ln of f x given theta prime is ln of f z x given theta prime minus ln of f z given x theta prime. Now, in the proof we have to take actual expectations, we might have to write integrals with respect to the densities. So, as I said, so far we have been abusing notation, the same f, this f is the marginal density of x, this f is the joint density of z and x, this f is the conditional density of z given x, right. This is a little abuse of notation and we have been using it, is always clear from context, but just to get more precise idea of these equations, let us write this a little more precisely. So, I put whatever random variable of which this is a density as a subscript. So, this becomes ln f x, x given theta prime is ln f z x, z comma x given theta prime, ln f z given x, z comma x theta prime. Once I put the random variables here, what I put inside should be small z, because those are the arguments of the density function. So, this is same as this is what we have been using intuitively so far. So, I just written it a little more precisely. So, this is the density of x, this is the joint density of z and x, this is the conditional density of z given x. Okay. So, let us remember this equation. Now, we take expectation of this equation with respect to the conditional distribution of z condition on x and theta k. This is our equation. So, on both sides of the equation of this term and this term, we take conditional expectation of this with respect to the distribution z condition on x and theta k. Okay. Because expectation is linear operation, conditional expectation of this will be conditional expectation of this minus conditional expectation of this. So, first, if I take the left hand side of our equation is this term, right. So, if I take the conditional expectation on the left hand side, this here I want to take expectation of all the z variables with respect to some distribution, but this is just a log likelihood of x. So, it does not contain any z's. So, obviously, it is just itself is a constant with respect to this expectation. My second term is log likelihood of the joint density. The conditional expectation of the log likelihood of the joint density is by definition my function q. So, if this is log likelihood of the joint density at theta prime, then because I am taking conditional expectation condition on theta k, this becomes q theta prime theta k. So, by definition the conditional expectation of the second term is q theta prime theta k. So, let us go back to that equation. So, conditional expectation of this would be itself, by definition conditional expectation of this is q theta prime theta k, and now I have to do conditional expectation of the last term. Okay. So, let us do the conditional expectation of the last term. So, for the final term, I want conditional expectation of log f z given x theta prime, right. So, this has to, I have to take conditional expectation of this quantity with respect to this density is written here. So, it will be some integral of ln f z given x theta prime, and the density is f z given x theta k, right. That is the density with respect to which I am taking the conditional expectation into dz. So, for the third term, this is the conditional expectation, we do not know what it is. So, let us just give a name to it, right. It is a function of both theta k as well as theta prime. So, let us call it r theta prime theta k. Okay. We will come back to this function a little while later. So, what have we shown now? By taking the conditional expectation, the first term was itself, that is the log likelihood of the incomplete data. So, ln f x of x given theta prime, this term conditional expectation was q theta prime theta k, and this term we just given a symbol r theta prime theta k. This is true for all theta prime, right. We will come back to this equation, but first let us ask what can we say about r theta prime theta k. We can show that for any theta not equal to theta prime, r theta prime theta is less than or equal to all theta theta. That is, r will have maximum when both its arguments are same. Okay. Recall r theta prime theta k, or r theta theta prime is this, where if I want to write a theta theta prime, this will become theta and that will become theta prime. Okay. So, this is r theta theta prime, and what we are going to show is that r will attain its maximum value if both the arguments of r are same, then its value is same as if I keep one of the arguments same and change the others. Right. So, for any theta not equal to theta prime, r theta prime theta is always less than or equal to r theta theta. Okay. Let us show this first. This is useful for our final proof. To show this, first we will show some other auxiliary thing. We will show that given any two densities P and Q of some random variable z, ln Pz Pz dz is greater than or equal to ln Qz Pz dz. So, if I am this Pz dz essentially means I am taking expectation with respect to Pz, taking expectation with respect to Pz, if I do it of ln Pz is always gives me higher value than ln Qz. Okay. So, for any two densities Pz and Qz, we are going to show that integral ln Pz into Pz dz is greater than or equal to ln Qz into Pz dz. To show this, we use this one standard inequality in expectations, what is called Johnson's inequality. I suppose many of you would have come across this, but anyway I will state it first. For any random variable y and any convex function f, expected value of f of y is greater than or equal to f of expected value of y. If f is a convex function, then Johnson's inequality states that expected value of f of y is greater than or equal to f of expected value of y. For example, x square, that is f x is equal to x square is a convex function. Then what this will tell me is the expected value of y square is greater than or equal to expected value of y whole square, right, which we already know, because expected value of y square minus expected value of y whole square is the variance of y, which you always know is greater than or equal to 0, right. So, that is the easy way to remember Johnson's inequality, but Johnson's inequality says that for any random variable y and any convex function f, expected value of f of y is greater than or equal to f of expected value of y. Okay. So, let us say y itself is a random variable which is function of the random variable z, right. So, take y is equal to some h of z and let Pz be the density of z. Then I have to do expected value of f of y and f of expected value of y. So, expected value of f of y, f of h of z, Pz dz. So, expected value of y can also be written as hz Pz dz, because y is equal to hz. So, expected value of f y will be integral f of hz Pz dz. It is always greater than or equal to f of expected value of y, f of integral hz Pz dz. This is true for any convex function f and any function h. Okay. So, now we will intelligently choose the functions h and f. So, we take hz as the function qz by pz, where both qz and pz are density functions, okay. And we take fx to be minus ln x happens to be a convex function. So, we take fx to be minus ln x and hz to be qz by pz. Then what will this become? Minus ln, that is function f, of hz is qz by pz into pz dz is greater than or equal to minus ln of integral hz is qz by pz into pz dz. Now, the pz's will cancel. So, it become minus ln of integral qz dz. Now, qz is a density function. So, integral qz dz will be 1 and minus ln of 1 will be 0. So, what this tells me is integral minus ln qz by pz into pz dz is always greater than or equal to 0. So, if I expand this, I get minus ln qz plus ln pz whole into pz dz is greater than 0, right, which means ln pz pz dz is greater than ln qz pz dz. That is what we wanted to get. Ln pz into pz dz is greater than ln qz into pz dz. Why did we want to prove this? Let us look at r theta theta prime. It is ln of some density into some density dz. If theta is equal to theta prime, the two densities are same. If theta is not equal to theta prime, the two densities are not same. So, I can think of theta prime as pz, this density, this conditional density when the value of theta is taken to be theta prime as pz, when it is taken to be theta as qz. Then this becomes ln qz into pz dz. what will be our theta prime? It will be ln pz dz. Right. So, combining with this and looking at this form is ln of one density into some density dz, and the two densities become same if theta is equal to theta prime, they are different if theta is not equal to theta prime. So, that gives us r theta prime, which is ln qz pz dz, is always less than or equal to r theta, which is ln pz dz. Right. So, for any theta not equal to theta prime, we showed that r theta prime less than or equal to r theta. Okay. Having done this, now we are almost complete with our proof. To show that the EM algorithm improves the likelihood, each iteration improves the likelihood is what we have to show. So, that means the log likelihood with theta k plus 1 is greater than the log likelihood at theta k, yep, because theta k to theta k plus 1 is my kth iteration. So, ln fx x given theta k plus 1 is the log likelihood value at theta k plus 1 is greater than or equal to the log likelihood value at theta k. We have shown earlier that for any theta prime, the log likelihood value can be written as q theta prime theta k minus r theta prime theta k. Right. So, when I put theta prime is equal to theta k plus 1, I get q theta k plus 1 theta k minus r theta k plus 1 theta k. When I put theta prime is equal to theta k, I get q theta k or theta k theta. So, if I do this difference, I will get the difference in likelihoods is these two terms. The first term is q theta k plus 1 theta k minus q theta k. Second term, these two will reverse, because in the expression for log likelihood, it is q minus r. Right. So, this becomes r theta k minus r theta k plus 1 theta k. Now, we can show that both these terms are greater than or equal to 0, and hence this is greater than or equal to 0. Why are both terms greater than or equal to 0? The m step of the EM algorithm is maximizing q theta k over theta, and by that maximization it came to the value theta k plus 1. So, obviously, the m step will ensure that q theta k plus 1 theta k is greater than q theta k. Here we think of theta k as any other value. So, in the function q theta comma theta k, if I put theta is equal to theta k plus 1, I should get the maximum value. So, in particular, instead the starting point was theta k, my ending point theta k plus 1 should be at least as good or better. So, q theta k plus 1 theta k minus q theta k is greater than or equal to 0. The Jensen's inequality, as we just now shown, shows that r theta k minus r theta k plus 1 theta k is greater than 0, unless theta k plus 1 equal to theta k, which will happen only if we can't improve q any further. Right. So, putting both these things together, we know that every iteration of the EM algorithm will improve the original log likelihood. So, this shows that every iteration improves the log likelihood. So, this at least shows that the EM algorithm acts as a gradient ascent on the log likelihood that ML estimates want to maximize. Okay. So, this assures that every iteration I am improving the log likelihood. So, hopefully, I will go to a local maximum of the log likelihood. The last step can be shown, it's a little technical, but so we will leave the proof of that. Okay. Hence, each iteration of EM algorithm is like a gradient descent step on the log likelihood. Okay. That's nice. So, that is the reason why essentially whether you use the partial derivatives of the log likelihood and use an iterative scheme to solve that, or use EM algorithm, we got exactly identical algorithms. Okay, as I said that each iteration improves does not necessarily mean we will converge to a local maximum, but as mentioned EM algorithm converges to maximum and finally general conditions. So, there is one small difference here, unlike in the simple density models that we have seen earlier in our earlier maximum likelihood examples, they are all going to the global maximum of the log likelihood, because those are all single maximum functions. Here, because we are essentially using gradient descent, we can only guarantee convergence to a local maximum of the log likelihood. Okay. This is in general true whenever we are using numerical techniques to optimize the log likelihood. Though this is a convergence only to a local maximum of the log likelihood, in practice EM algorithm is very effective for estimating mixture densities. It is very often used for estimating mixture densities. In practice, it converges fairly fast. And of course, as I said, it is also important in many other probability models, such as what are called hidden Markov models, graphical models or Bayesian networks and so on. Many of these things we may not consider in this course, but the EM algorithm is still a useful algorithm to know, and that is why we looked at that. As I said, when we started the EM algorithm, this is the last topic we look at in estimation of parametric, that is parametric estimation densities. So, this completes our discussion of density estimation under parametric models. Okay. So far we have been considering what is called parametric estimation techniques. What is parametric estimation? We assume a density model. By assuming a density model, I mean we assume that the density is Gaussian or density is exponential. So, we know the form of the density. What we do not know are the parameters of the density. Okay. So, we are only doing parameter estimation. So, we could assume a density to be either Gaussian or exponential or gamma or T distribution or what have you, or even mixtures, as we now know how to do it. And then we are essentially estimating the parameters, whether it is the Maxent likelihood method or the Bayesian method is for parametric estimation of the density methods. Now, let us say we do not want to assume any form for the density, we do not want to assume any parametric form for the density. Can we still estimate the density function? We have no clue as to the form of the density, but we still somehow need some method of calculating the density value at any given x. When we say estimate density, we do not have to write it as a single equation or anything, but ultimately if I want to implement the Bayes classifier with the estimated densities, what I need to do is in practice, whenever you give me a particular feature vector to classify, I should be able to calculate the value of the density function at that particular feature vector value. So, we need an expression that given any x will give us the density function f x. So, that is what we want to estimate without assuming any parametric form for the density. This is called non-parametric estimation. Okay. So, that is what we are going to look at. So, to go there, let us first consider one dimensional case. So, you have a single random variable. I have a sample x1, x2, xn which are IID from some density f x, and I want to estimate the density f x. We do not know the form of f. How can I estimate or store such a density? I know nothing about the density. One way I can think of doing it is if the density is sufficiently smooth, then it does not vary too fast. So, I can say on any small interval, I can think of the density function value to be constant. If the density, if I am thinking of density as a smooth density and hence it does not vary too fast, then on any sufficiently small interval, I can assume the density to be constant, which means I can try and estimate approximate the unknown density by a piecewise constant approximation, as I am thinking of f x as a piecewise constant function. So, I can have many intervals, and on each interval it will have a constant, maybe on different intervals different constants. So, that is what is called a piecewise constant function approximation. Okay. This will be like what if you are given a okay. I will come to that a little later. How do I get piecewise constant approximations? Essentially, we cut the x axis into small intervals. If you still remember how your integration theory, when you are defining a definite integral a to b f x dx, you take the interval a to b, cut into small intervals, and then approximate the area under the curve by those upper rectangles and lower rectangles. So, essentially a piecewise constant approximation is like this. We cut the x axis into small intervals and build a function that is constant on each interval, that is essentially some value of the function within that interval, right. And then that is how I can build a piecewise constant approximation. So, if the function f x, which is a density, is constant over some interval a to b, then if I integrate the density over a to b, I get probability x is between a and b, that will be that constant times length of the interval, right. And the probability that x is between a and b, how do I calculate that? If I have a large number of data, then I see how many of them are between a and b, that should be that fraction of data that have fallen in the interval A to B would be a good approximation to that probability. So, if I have a large number of data for any interval A to B, I know how many what fraction of the data has fallen in that interval. So, divide that by the length of the interval, I get the value of the density within that interval, which is the constant I want to approximate it with. So, what does this mean? That we are essentially approximating F by the histogram of the data. So, I am cutting x axis into intervals and I am building a histogram of data. Histogram simply tells me what fraction of data is in each of the intervals, right. So, that histogram is essentially what gives me the density function, right. So, here is a simple example. So, I cut the x axis into some intervals, there are 11 intervals here. So, this is some arbitrary density function, right, some multimodal density function. So, I have taken some data and built a histogram for the data, and that histogram approximation turns out to be this. Of course, it is not very great, as you can see, it misses the value of the function badly at some of the points, right. As you know, any such histogram can be improved if I make a finer interval. So, instead of taking 21 intervals, 11 intervals, if I take say 21 intervals, we can get a better approximation. Here is a better approximation, right. If you look at this, this is a little crude approximation because the interval lengths are large. On the other hand, this is a more finer approximation. As you can see this peak, around this peak we got the values much closer now than last time by simply having our bins more. So, if I get more and more bins, obviously I can get better and better approximation, but the price I pay is that ultimately how am I going to store the density? So, I have to remember all the bins and then all these constant values. I have to remember the entire histogram. More the number of bins, the larger the histogram. So, I need more memory to store store my approximate density. Of course, I can improve the approximation. Of course, I do not know because original density I do not have. I do not know which length of the interval is right. And of course, I know smaller the length better it would be in the approximation, but if I make it too small, then it is very difficult to store. Also, if I make it too small, suddenly some of the intervals may have 0 points, right. If I have 10,000 intervals and if I have only 1000 points, most of the intervals will not have any points, right. So, making the intervals too large also will not work, okay. But all this apart, this is a simple idea for approximating a density function without assuming any form for the density function, okay. Of course, you can't simply extend it. If you extend it in a very simple minded fashion, saying in the dimensions. So, in 2 dimensions, I will cut x into intervals, y into intervals, and so each pair of intervals will give me a small rectangle and I use that as the bin size. Then in d dimensions, my bins will grow enormously. If I have got n bins in 1 dimension, in 2 dimensions will be n square and will be n to the power d in d dimensions. So, if I want even 10 bins for a 50 dimension, 100 dimension feature vector, say 100 dimension feature vectors are very common in pattern recognition, I get 10 to the power 100 bins to store. It is just even with today's modern cheap storage, that is enormous amount of storage to have, right. So, the number of bins grows very exponentially, and as I said, if I have 10 power 10 bins, I will not have 10 power 10 data. So, most bins will be empty. So, I will not even get a good estimation, right. This is essentially what is called curse of dimensionality. We can't simply estimate it by such piecewise constant things very easily, okay. So, as the dimension grows, no amount of data will be sufficient to completely cover the space. Okay. However, the basic idea of approximating the density by a constant over a small region can be made to work. Okay. That is what we are going to look at. What we are going to do is, we do not have to actually put these bins all over the place, right. We know we have some information only wherever there are training samples, where they are in the regions of the feature space where we do not have any training samples, anyway we have no knowledge of the density. So, if we can find a nice method of erecting beans only around the training samples, right, we can still make this basic idea to work. Okay. So, that is what we are going to look next. How do we do this? Let us say given any point x in the feature space, let b of x be a small region. So, for example, a small sphere with x at the center and a small radius. So, b of x denotes such a region around x, and let rho be integral of the density over b of x. So, this is actually the probability that a random sample will fall in the region b of x. Okay. If f is nearly constant over b of x, then in this integral I can take the value of f x prime to be the value of it at x. We assume because x is around, x will obviously in b x because b x is in around x. So, I can over this region I can approximate f x prime by f of x. So, this rho becomes approximately equal to f x into integral of dx prime over b x, that is nothing but the so called volume of that region. So, rho becomes approximately equal to f x into v, or f x becomes approximately equal to rho by v, right. So, if I take a small region of volume v and assume that the region is small enough, so that f x can be approximated as constant, then f x can be approximated by rho by v. So, I can take b x of known volume. So, the question is how do I get rho? Rho is this integral. Of course, I do not know f, so I can't directly calculate the integral, but I get rho from the samples. Suppose out of the n IID samples, k samples fall in Bx. For any arbitrary sample, probability that if I take any one sample, any one iteration of x, the probability that it falls in Bx, because Bx is the falls in Bx is the integral of the density function over Bx. That means, the probability is rho. Because these n samples are independent, it is like n trials where the success is falling in Bx and failure is not falling in Bx, which means k is binomial with parameters n and rho. Okay. A binomial random variable parameters n and rho has expectation n rho, and binomial density for large n is very sharply peaked around its mean. So, I can take the mean, which is n rho, to be a good approximation to the random variable k. So, I can take k to be approximately equal to n rho, or rho to be approximately equal to k by n. This is intuitive. Rho is the probability that a random point drawn from this density will be in the region Bx, and we have drawn n points, of which k have fallen in the region. So, k by n is a good approximation to the probability. So, combining these two, f x is rho by v, rho is k by n. So, f x is approximately equal to k by n v. Okay. What does this mean? If I want the value of f at any given x, I erect or I take a region around that x of volume v, count how many samples have fallen in it, let us say that is k, then I can approximate f by k by n v, right. This is essentially generalization of our binning idea, right, and this is the basic idea that we used earlier also, except that now we are very intelligently erecting our regions only where we want to calculate the density. So, at any x, if you want the density value, we take a small volume v around x and count the number of data samples that fall in this region. This gives approximate value of f as above. Okay. Of course, this is too crude, we will formalize this, we will give you some systematic ways of doing it, but for all the formalization that we do, the approximations involved in this idea will not go away. Okay. So, let us just look at what these approximations are. Okay. The choice of v certainly affects the quality of approximation. So, we are saying if you want value of density at a point x, take a volume v around x, take a region Bx around x of volume v. So, what region I take depends on what value of v I choose. There are two conflicting requirements for v. For the approximation rho to be f x into v to be good, v should be small, otherwise assuming f to be constant over rho over Bx is not a good assumption. On the other hand, if V is very small, unless n is very large, k may be 0 most of the time, right. So, if V is very small, the probability of any sample falling there is so small that if for moderate n, I may not even have one sample falling there. So, for k by n to be a good estimate of this probability, k should be reasonable, which means V can't be very small. So, in practice, the choice of V is a compromise between these two requirements. We are going to put some nice models and equations around this concept, but ultimately this arbitrary choice of the volume element does not go away. Okay. It's a matter of practice, and for a given density, for the given data, we have to find what the good choice. But before we go there, obviously, as we seen, the how small V should be all depends on how large n is, right. So, all choices should be with respect to n. So, let us say V n is the choice of volume when we have n examples, and similarly, let us say F n is what is the estimate we get for the value of density at x when I use the n samples, and k n may denote the number of samples that fall into that volume out of n when I am using n samples. The reason for putting n as subscript is now I can ask, at least theoretically, if n goes to infinity, am I getting good estimate, right. So, we can ask, does f n converge to f as n tends to infinity. Basically, if that to happen, my choice should be such that the volume element should shrink to 0 as n goes to infinity. The number of samples that fall in the volume element should go to infinity. However, the fraction of the number of elements that form in the volume element have to go to 0. All are intuitive. Unless V n goes to 0, we can't get correct estimate, because ultimately assuming that f is constant over a region, and so unless the volume element shrinks to 0 in the limit, we won't get the correct value of f. So, that is very straightforward. If f is not equal to 0 at a particular x, then rho will not be 0, okay. Around any arbitrary this thing. So, as n tends to infinity, there is a fixed fraction that has to fall into that region. So, we expect k n to go to infinity, and obviously k n by n has to go to 0, because our density estimate is k n by n by V n. So, if V n is going to 0, k n by n has also to go to 0, otherwise the density estimate won't has no chance of going to any finite value, right. So, essentially this is some guidance of what should happen. So, depending on how large n is, we should take sufficiently large V n, so that both k n and n are of appreciable values, because we do have only finite data. So, that limiting case may not help us, but we choose a size based on n. Okay. Actually, there are two ways of doing this. One is we can fix a volume element V, as we have been doing so far, and count k. This is known as Parzen window or kernel density estimate. Or we can do it the other way, because we want k to be reasonable and we do not know what V will give k reasonable. We fix a k, and then given an x, we will ask how much volume do I have to include around x, so that at least k of them fall into that volume, right. This is called k nearest neighbor method. So, we will look at both of them, but we will first start with Parzen. We will just introduce Parzen windows in this class, and then we will stop. Then we will first consider Parzen window method. Let us say I define a function phi, which maps d-dimensional space, which is my feature vector dimension, to R, as phi of u is 1 if each component of u is less than 0.5, the absolute value of each component of u is less than 0.5, 0 otherwise. So, u I am using as a vector of d components u1 to ud. As per our notation, there are no bold letters to denote vectors, this is all from context. So, what is this phi u? It defines a hypercube in RD centered at origin. Along each of the coordinates, if you go beyond 0.5, then the phi value is 0, otherwise 1. It is simply an indicator for the unit hypercube in RD centered at origin. Also, because of the way it is defined, phi is symmetric, phi u is phi of minus u. Okay. Now, what will be phi of u minus u0 by h? u0 will mean translation, h will mean scaling, right. So, it will be a hypercube of side H centered at U0. Okay. All of us know this, if phi u is a hypercube, phi u minus U0 is the hypercube shifted to U0, and by H is it is scaled. Earlier it is of unit side. So, now it is side H. Okay. Let us say D is the data samples. Then for any x, phi of x minus x I by H, this would be 1, because this is a hypercube, because phi is symmetric, I can think of it as centered at x or centered at xi. So, let us say it is centered at x, right, and of side H. So, which means this would be 1 only if xi falls in a hypercube of side H centered at x. Right. So, if I take a hypercube of side H centered at x, if xi, one of the samples is within the hypercube, then phi of x minus xi by H would be 1. Which means, if I sum phi of x minus xi by H over I, which will tell me how many samples will fall within this hypercube of side H centered at x. This is what we have been calling K. Now, hypercube of side H has volume HD, putting all this together. So, this is the number of points, the sum over this 1 by H could have also come out of the sum. So, sum of this is the number of points, that is K, HD is the volume, N is the number of samples, K by NVN or K by NV was our estimate. So, I can write that nicely like this. Okay. So, if I know the function phi and if I store all the xi's and I make a choice of H, which is the size of my volume element, which is indicated the size of my volume element, then whenever you give me an x, a new x at which I have to calculate the density value, I can use this equation, calculate the density value. So, it is a nice way to write out our non-parametric density estimate, which is known as the Parzen window estimate. Okay. Of course, the Parzen window estimate used a particular phi, this hypercube. There are other phis. So, because it is a hypercube, there are some artificial discontinuities in a histogram. We can use other phis. So, what we will do next class is we will start from this Parzen window estimate and see, this of course is called Parzen window estimate, and we will look at what are the other phis we can use, what should phi satisfy. The particular hypercube we given is certainly one choice, there can be other choices, and then ask how good is such an estimate, does it at least asymptotically converge, and that will complete our kernel density estimates. Thank you.